Okay, so now I would like to explain why it is that we can estimate how an integral diverges just by dimensional analysis. So let's think about what's going on. So the integral that we do, I, is a function of only two dimensionful parameters. Okay, so the I will be a function of m squared that appears. That will be length to the minus 2, and it'll be a function of lambda, which is length to the minus 1. So for example, so let's say that I was dimension L to the minus n, then in general, you would learn that I is equal to some lambda to the power of n, but then we could have any function of lambda squared over m squared, for example, because lambda squared over m squared is dimensionless. And then, in fact, you simply could not tell how the integral diverges because there's all kinds of non-trivial dependence sitting inside f. So in general, you cannot tell what the divergence is, so what the power of lambda is. However, the divergence comes from very large values of p mu. So it's when the magnitude of the spatial momentum is of order lambda, and that means p naught itself is also very large. Okay, so where p and where the momentum is very, very large. Now, if the momentum is huge, then when you take a look at this propagator formula, if p squared is enormous, you can just forget about m squared. And that'll happen for every single denominator. So for very large p, for very large p, the dependence on m disappears. Okay? If you're at such massive energies, close to infinity, then you can just neglect the mass. This p squared minus m squared, well, the m squared, you can just forget about it. It doesn't even count. Okay? So so that in this limit, there is no dependence on m squared. So this extra function over here that may have been possible is no longer possible. And then I depends only on lambda. And because there's only one dimensionful parameter, it means that the dependence of I on lambda is dictated by dimensional analysis. By dimensional analysis. Okay, so this is the idea. So what are the key points? Well, naively, you could have had the dependence also on the mass squared. And then, as I've explained, that would have complicated the problem. But this dependence on the mass squared just disappears at very large momenta. And that's precisely the region that we're interested in. That's precisely the region where we want to estimate things. So we're not interested in the exact value of the integral. We're only interested in how it diverges. And if that's the information that you're interested in, you only look at the very large momentum contribution to the integral. And in that very large momentum contribution, you can forget about the m squared dependence. And in that case, the dependence of the integral on the cutoff is dictated purely by dimensional analysis. So if your integral was like length to the minus n, you know absolutely that I will behave as lambda to the n multiplied by some constant. And perhaps the only odd one out, let me just stress, of course, if I is L to the naught, it means that I behaves like log of lambda. And maybe I should say proportional to here. And you can check it. You know how to estimate the size of the integrals just by Wick rotating and then moving to a radius and an angle. So you can go ahead and check if this conclusion really is true. I've just explained to you why that conclusion is true. Okay, good. So now that we have some understanding of why it is that dimensional analysis determines the degree of divergence, let's now do a more careful analysis using dimensional analysis. So consider a Feynman diagram F, okay? And there'll be a few parameters which are important. We want to introduce the integer I, and I is equal to the number of internal lines in F. E is equal to the number of external lines in F. So, I mean, here's just an example. I think you know what we're talking about, but always good to have an example in mind. For this Feynman diagram sitting over here, there would be 3 internal lines because there's 3 lines that stretch between vertices, and there would be 2 external lines because there are 2 lines that connect to the external points. Okay, and then we could denote by n is equal to the number of vertices in F. And here n is equal to 2. Now we're going to be slightly more general. Let's say number of vertices in F with R legs. So for this particular example, R is 4. Each vertex has 4 legs connecting to it, okay? But in general, we could consider phi R. In that case, so we have a vertex that perhaps looks like this. If we were labeling the legs, this would be 1, 2, 3, 4, going all the way up to R. So for the vertex that we're considering with R as 4, we'd go 1, 2, 3, 4. So this is why R is 4. And then let me also say that the interaction vertex would be an integral d dx in d dimensions of some coupling gr times by phi to the power of r. And it's going to be useful to keep this generality. So let's also introduce d, which is the number of space-time dimensions. Okay. And then finally, we will also want L, which is equal to the number of loops. Good. So now in terms of these numbers that we've just introduced, let's state what integral we're interested in studying. So I is equal to, so if we've got L loops, we'll have an integral dd p1 over 2 pi to the d. We'll have one of these integrals for each of the loop momenta. So we'll have an integral dd pl over 2 pi to the d. And then we will have a propagator for each internal line. So this will be, I'm going to put p star 1. It'll be some momentum. It won't actually be p1 or p2 or up to pl. It'll be some linear combination of loop momenta and external momenta. But I'm labeling it here with a 1. This is the first denominator. And then it will continue up to I over, and this will be the ith denominator for the ith internal line. And this is plus I eta. Okay, so that's what we want to estimate. So let's just be completely clear on this. Let me give an example. Imagine that you were studying this Feynman diagram, okay? So we would have a momentum k flowing in and then k flowing out. We could have P1 flowing at the top. Actually, let me put P1 flowing into the vertex, okay? You know what? It's going to be useful to have a different color. So let's imagine that we've got P1 flowing into the vertex. We've got P2 flowing into the vertex. And then flowing out of the vertex over here, we would have K plus P1 plus P2. And you can see that the assignment of momenta is entirely consistent with momentum conservation. Okay, then what is the value of this Feynman diagram equal to? I think now you can almost do this in your sleep. So there would be minus IG z squared 4 factorial squared. There's no closed lines, no equivalent vertices, no equivalent diagrams, but there are 3 equivalent lines. It'll be over 3 factorial. Then we've got an I z inverse over a squared minus m squared plus I epsilon, and an I z inverse over k squared minus m squared plus I, sorry, eta. I'm trying to say plus I eta everywhere because we've used epsilon. Okay, good. And then this is multiplied by the integral over the loop momenta. So we'll have an integral, the 4p1, there's 2 loop momenta, over 2 pi to the 4. So I've said d is equal to 4 here, okay? Our analysis is going to be for general d, so that's d is equal to 4. And then we will have I z inverse p1 squared plus m squared plus I eta. There's the first propagator. I z inverse p2 squared plus minus m squared. What am I doing? Okay, so minus m squared, minus m squared. So let's correct those signs. Good. And then we've also got I z inverse. It'll be k plus p1 plus p2 squared minus m squared plus I eta. Okay, so this is what the diagram looks like. Now, these pieces over here, okay, so here we've got a piece involving the coupling and the combinatorics, and here are some external lines. Who cares about those? The divergence isn't coming from there. The divergence is coming from this extra bit here that I've bracketed in green. So this, to get that green bracket, you strip off the coupling dependence, the combinatoric dependence, and the external lines. And that's actually what we're studying in this integral I when I write down I here, okay? It's that piece of the integral. That's what we studied before. Good. And for this diagram, of course, we know that there are 3 internal lines. That's why sitting here, we've got 3 propagators. And you can see it's P1 squared, P2 squared. And then this one is not related to one of the momenta that we're integrating over. It's some linear combination. And we also know that there are 2 loops. So 2 loops. So here, this is here because we've got 2 loops. And this is here because we have 3 internal lines, okay? And that illustrates this formula underlined in green that we're trying to analyze. Great, we'll keep going in a moment.